Okay, thank you so much, Rain, for a brief introduction. My name is Teshome. Basically, I'm a postdoc PhD in University of Coimbra here in Portugal. Today, I will talk about power analysis and sample size calculation, and I will try to show the analysis using freely available software like RNG Power. So yeah, you don't have to expect me to talk everything about sample size and analysis within an hour, and I will give you a high level and a brief introduction about these topics anyways. So saying this, let me jump into the flow of my talk. I will start that why does sample size matters, why we are concerned in the first place, why we don't start from two observation or maybe five, 10, or maybe 100, or maybe even a million, why we are bothered about sample size issue and why we bother about the power in the first place. So I will tell you the reasons behind. And again, what are the possible factors that are very important that we have to know when we are dealing with sample size calculation? And again, I will show you some demos for common study designs when we calculate a sample size for a certain study and using RNG power. I basically choose independent t-test. You can think of it the paired test and other statistical tools. One way, ANOVA, MANOVA, linear regression, and some kind of fancy models or maybe advanced models. And you can stick to simulation when G power and R power are not feasible. And finally, I will tell you some final message that you should have to keep in mind when we are talking about sample size determination. And the first and the very important reason why we are bothered about sample size is that it ensures studies have adequate power. So if a certain study have adequate power, that means we can feasibly detect the effect if it exists actually. So the second reason that it can balance a scientific rigor with a practical constraint. Sometimes there is a trade-off that there is a budget constraint in terms of time, in terms of fund, in terms of participant. So we should have to balance this trade-off. So we should have to stick to the scientific principles and we should have to calculate the sample size and power in advance. And again, we can think of it in terms of ethical dimension as well. It can avoid exposing participant to research that without sufficient benefit. Uh, if we are able to detect an effect using 100 patients, for instance, why we are exposing our patients, or maybe why we are recruiting a million or maybe 2,000 patients. So we should have to consider as the ethical dimension of conducting our study as well. If I try to explain this stuff a little bit in detail, if our sample size is too small, technically we can say that it is very underpowered. So if it is underpowered, it may fail to detect a statistically significant effect, although the effect exists. And again, it may further reduce the probability that a statistically significant result reflect a true effect. This means that we get an information from few observations and we may estimate some parameters and may conduct some hypothesis that is good and smart. But at the same time, if somebody repeat an experiment in different setting, it may lead to different conclusion. And again, in that regard, to get the published results, people may switch to some questionable research practice like p-hacking, exaggerating the effect size, and this leads to a reproducibility crisis, which is the current topic everybody is discussing now. And on the other extreme, if we do have very too large sample size, in most of the cases, this is good if we have uh, enough fund actually, and we call it the study is overpowered. And but sometimes this also leads to unnecessary waste of resources like animals, humans, and you can think of it that if you are conducting some clinical trials, the Declaration of Helsinki. So there are some principles should be followed if we are conducting some medical research involving human subjects. So first, we should have to get a consent from the subject in the first place, and at the same time, from legal point of view, we are not basically allowed to expose a certain patient to extra side effect if we manage to yeah do an experiment on 10 mice, for instance, while we need to recruit 1,000 or maybe million mice. So and again, one of the advantage of having overpowered study is that it can act as a magnifying glass to detect a tiny effect. That's good. But the same at the same time, as a researcher, we should have to ask ourselves, is this relevant to deal with? Is this effect is biologically significant? Is this effect is clinically significant? So we should have to think of it that before recruiting our staff. So in two ways, there are some pros and the cons. So what are the key elements that we should know when we talk about sample size? Basically, we should have to know four basic elements that are possibly affecting our sample size calculation. Basically, the first one is the very effect size. That means the type, the nature, and the magnitude of the effect size is very important. When we say effect size, it is simply the magnitude of the difference between the null hypothesis and the alternative hypothesis. So if we are trying to specify this effect size in advance to calculate our sample size for a certain study, a priori, where do we get this number? This is a critical question that a researcher should ask himself, the first one. It is very important at the same time. It is not simple question to answer at the same time. So there are different ways to get this number. The first one is you should have to get an expert opinion if somebody is around and knows in detail about the subject matter. Yeah, we can get it that number from that guy. That's good. Again, if you do have enough time and enough fund, you can also conduct a pilot study, and from that we can estimate some number, and you can use it that number as an effect size. Otherwise, you can rely on existing studies and conduct some meta-analysis, and from that, that summary statistics can be used as an effect size. So finally, if you have no option, you can consider some suggestions and numbers considered by coins in and just this is basically implemented in psychology, but it may be different in biological science, in economics, or maybe in medical science. So when we use these numbers, we should have to be very careful, but these are the benchmarks that we can use if we have no option. Basically, maybe if you are conducting a t-test, probably comparing two means, small is considered as zero point 0.2, medium is considered as zero point 0.5, and large effect size is considered as zero point 0.8. So f-test, and maybe for ANOVA, for regression, for correlation, and maybe for chi-square test of independence, and you can check it out. And I would suggest that use these things as a starting point. So otherwise, just stick to the pilot study or maybe conducting a meta-analysis. Yeah. And the second very important factor that determine our sample size is statistical power. So statistical power is simply a probability. Probability of what? It's probability of uh, just detecting a true effect if it really exists. If it does not exist, it doesn't matter actually. And conventionally, a power of greater than or equal to 18% is considered as a sufficient power. And if you want, mostly in medical science, they push it up to 19% and 95%. That's good. But at the same time, you should have to think of it your cost, and you should have to push it up your sample size, because it may require a larger sample size. And thirdly, we should have to think of it a significance level, which is a type 1 error. Basically, it's a probability of rejecting the null hypothesis given that the null hypothesis is actually true. So we are committing a mistake. So we basically set this type 1 error into 5%, which is set by Fisher. And in economics and in behavioral science, they put into 10%. But whereas in medical science and in very strict sciences, they put it 1%. But whatever the case, for today's talk, let us stick to 5%. So to summarize what I'm talking, that if your decision is failing to reject H naught while the H naught is true, yeah, you are not committing a mistake. We are making a correct decision. We call it a confidence level. And again, if your decision is rejecting H naught while it is true, yeah, you are by default committing a mistake, which is a type 1 error. We should have to set it in advance as 5%, let it be. And again, if you are failing to reject as a researcher H naught, where H naught is actually false, you are committing a mistake, and which we call it type 2 error in statistics. And again, if your decision is rejecting H naught while H naught is false, basically you are not committing a mistake, and that is a correct decision. We call it the power of the test, the power of the. So if I put it all this stuff in one slide, I should have to know power, sample size, significance level, effect size. If I know three of these two, these four, I can possibly calculate the other one. Most of the time, we stick to calculating power or maybe sample size. So in one way or maybe other way, these are the main concepts we should have to know when we talk about sample size. Sample size. Excellent. Now I will directly jump to showing some example using G power and R very quickly. And so that if you have any question, you can put on the chat box and I will try to explain it today, or maybe you can also send me through my email. So the first test I choose because everybody is familiar with it and easy to explain, and is independent t-test. It's basically a statistical tool that help us to compare two groups and the control and the treatment. For instance, the actual fertilizer and the new fertilizer, I would say, the control treatment with a new drug, I would say. So these two groups are basically independent. I will calculate the summary statistics, and as a researcher, I will ask myself, is this really two groups are statistically different? That is the question I have in mind. Okay, if this is my question, how many observations do I need to find a meaningful difference between these two groups? That is the thing that I'm thinking at the back of the screen. So to explain using my example, there is a pharma company wants to test whether a new drug reduces a blood pressure compared to the existing one or maybe the placebo. They also plan to randomly assign hypertensive patients to either the treatment or the control group. I highlighted randomly because it is a very important concept in statistics. Randomization by itself reduces bias. So yeah, putting or maybe allocating our patients randomly to the control again and the new treatment is by itself, which we recommend mostly. So they do measure the blood pressure reduction after 8 weeks, and they come to me, or maybe they come to you, and how many patients do we need to just recruit to detect a meaningful difference between these two treatment and the control. So I don't have any prior information. I don't have any guy who's expert around me. So I don't just didn't find any literature. So the only thing that I should have to do is conducting a pilot study. Then I recruited just 14 patients, which are 2020 for each group, and I calculate the mean for the control group is 5 with a standard deviation of 12, and the mean for the treatment is around 12 with the same standard deviation. So this is very hypothetical, guys, and it's nothing to do with the reality. I come up with this number for sake of demonstrating my example. So from this, I try to calculate coincidence using a standard formula. So you can basically refer a standard statistics book how to calculate the coincidence, and finally end up with 0.58. So if you see the treatment mean is 12, which is by far greater than the control mean, which is 5. So I can think of it that the treatment drug is doing well. Is it really significant? So that is the test I'm trying to test. So before I jump to just showing you the result, whenever you try to use the G Power, by the way, G Power is a free software that is freely available and designed by people from the University of Düsseldorf. I don't know how to pronounce it with all due respect, actually, which is based in Germany. And the page looks like this one. You can freely download it here for Windows and for Mac, whatever you like, and there are a lot of versions. So I will back to my talk. So this is the first main window that you can find when you launch your G-Power. I already installed on my PC. Then if I click it on my G-Power, I will get it this page. So there are some main windows or maybe components that you can think of it. The first thing that you should have to check it this way. This is the place where that you can test or maybe choose the test family. Are you conducting F test, T test, chi-square, or maybe Z test? Very limited in G power actually. And again, the second component is the place where you choose the statistical tool. So out of these options, which you are going to do. In my example, I'm going to do two independent t-tests. And again, thirdly, am I calculating the sample size or maybe am I doing the power analysis? This is a place where I'm going to choose the available options here. For a time being, am I going to calculate the sample size given alpha, power, and effect size? Perfect. I will choose the first option. And here is a place where I'm going to set or maybe put some parameters. Is my test is one-sided or maybe two-sided? Do I have my effect size? What is my alpha? What is my power? And is my state is balanced or maybe unbalanced? So these are the place where I'm going to fix. So by default, my test is two-sided. You can make it one-sided, by the way. And my effect size is 0.58. Just you can fix it here. And I will set it my alpha, which is a type 1 error, into 0.05. Here we go. And my desired power is the default is 95%, but let me put it 80%. And an allocation ratio, which is equal to N2 over N1, is equal to 1, which implies that I'm using the same number of observation in each group, which is technically a balanced design. So I will keep it as 1. So this is a place where you set the number of or maybe the parameters required to calculate your sample size. And finally, if you click it on the calculate, you immediately get some graphs, which is the underlying statistical matter that explain how alpha is described, how beta is described in connection to the power. So you don't have to bother about this picture actually. And the important thing is that sample size for group 1 is 48 and sample size for Group 2 is 48 because my design is balanced. In total, I may need around 96 patients to get a meaningful effect between the treatment and the control group. And this is the way how we can approach using a GPAR. So here is my explanation, what I already showed you. So at home, you can simply exercise by your own. But one question I do have here is that if I change the allocation ratio N2 over N1 to 2, for instance, what would happen? The study may be unbalanced design. And do I may need a large sample size or maybe small sample size? So it is highly likely that I need just large sample size, and I will leave that as an exercise for you. Okay, what if I just do the same exercise using R? Basically, R is a free software and you can download it and you can use it at home. And when you deal with R, which package is important? Yeah, if you freely Google it, you end up that Power package is the first one pops up, but we also have ample of package that helps to calculate power. And install it that one and load it that package. And in that package, there is called power.ttest function, and that specifically deal with independent t-test. So I do have some argument in this function. The first one is n, d, significance level, power, the type of test, and again, the nature of your hypothesis, one-sided or maybe two-sided. Once you set all this stuff, you can put it n is equal to null. That is the quantity I'm going to calculate using my R actually. And once you set everything, simply you can run it and you will find it around 47.6 for each group. So if you multiply it by 2, you exactly get 96 that we get using GPAR. Using GPAR. So I saw some message. If that is for me, I may ask for your opinion on the appropriate effects of um, I don't know exactly what vitro study is. Is something yeah, an animal study, right? I'm not an expert in that area, but um, more or less it is related to clinical study, I guess. Uh, yeah, I strongly suggest that conducting meta-analysis is the best strategy for me. It may work well for me, but in your case, I don't know. I don't know. I don't just exactly know what vitro is basically, so uh, I prefer not to comment basically, rather than just mixing up everything that I don't know. If there is no question, I will jump to the one-way ANOVA. Yes, you can think of it that the paired t-test, the one sample t-test, and you can explore it by your own. And the second one is one-way. Okay, t-test can help us to compare two groups. What if I have 3 groups, 5 groups, or maybe 10 groups? That is a place where ANOVA is very helpful. So what I have control group, drug A, drug B, drug C, then I can test it. The whole group is statistically different. Once I know the whole group is statistically different, I may conduct pairwise tests if needed once I reject the null hypothesis. So here, my example come up with a clinic wants to compare the effectiveness of different treatments for chronic back pain. There is a physical therapy and they will give some medication, and again they also give a combined therapy which is physical plus medication. That's good. Now they try to measure the pain reduction after 12 weeks, which the scales run from 0 to 100, where numbers close to 100 are just the drug is or maybe the therapy is doing well. Now, they will ask you again how many patients do they need to do this stuff, and they wanted to know their sample size and their budget in advance. Again, I will rely on my pilot data, and I recruited again around 15 for each group, which is 15 times 3, which is around 45 patients or maybe humans, I would say. And again, with all due respect, again, I come up with some hypothetical data, not real. The mean for therapy is 22, 25, and 34. From this simply summary statistics, I would say the combined therapy is doing well. And I'm asking myself, is it really good? Or maybe is it really out? Do I get the same result if somebody repeats the same experiment? That was the question in mind. And again, for that, I should have to know my sample size. So when we do an ANOVA or maybe MANOVA, the common effect size that we can use is Cohen's F, which we do calculate, and we do have a standard formula to end up with. So I simply hide it or maybe avoided that part, and I get it 0.33. So you can simply calculate that number or maybe get this number from this observation. Great. So how we can get it? I will stick to my G power, which can give me very quickly. So I said that I should have to choose the type of test that I use. Usually I may stick to my F because when I'm just talking about ANOVA regression and full model, F test is the thing that I'm talking with. And on statistical test, I should have to choose the fixed effect for the overall model and for one way ANOVA. And here again, I'm going to calculate the power, not the power, sorry. I am calculating a sample size given alpha power and effect size. By the way, you can also switch it and calculate the power. It's very easy. And you can set it, the parameters here. And I usually put my power with 80%. You can make it 19. In that regard, your power goes up. Your sample size goes up. And again, you should have to think of it, your budget and your cost at the same time. And I do have three groups: the physical, the medication, and the combination of the therapy. And that is the three. And if you simply click on the calculate, you end up with a total of 93 patients are needed to just see if there is a significant difference between these two treatments. So if you divide 93 by 3, you will get it 31 for each group. 31 for each group. So if you switch to your R software, you can use it, a package called Power again. I'm getting some message. Not for me. Okay. Okay. Thank you, Ren. I think Ren is helping me to answer. Thank you so much. And you can set it n is equal to null and f is 0.33, and the basic thing is you should have to use power dot ANOVA test. So if you have you already installed your R, you can say it help uh, um, just simply before ANOVA uh, test. Just if you click it on this, you can get it, the function I'm talking actually. Yeah, you can read it here. Power calculation for balanced one-way analysis variance, and what is K, what is N, what is F, what significant. Yeah, you can read it here. So I'm using this function, and I'm set my parameters, and what I can do is simply running, and I end up with 31 patients for each group, 31 for each group. Um, Okay, the third one is a linear regression. As everybody knows that in linear regression, we do have one outcome and we do have some covariate, whether they are continuous or maybe a categorical in nature. We try to see the effect of this covariate on our outcome. So when we fit a linear regression, we do have some interest. The first one is R square, which is a coefficient of determination, which may tell us how many variations of our dependent variable is explained by those covariates. That is the first thing that we should have to be just some may be interested on that. And at the same time, you may be interested to see the effect of a certain covariate on our outcome by controlling the other covariate or maybe other predictors. So we can think of it calculating a sample size for detecting a significant coefficient of determination. What if I may include all covariates? Do I may get large R square? That is maybe if that is your research question, or maybe what is the effect of x1 on my outcome, my y, after controlling other covariate. So that is the sample size that you are looking for to detect the significant regression coefficient. So we treat differently this stuff in linear regression. So to justify or maybe to explain my stuff, there is an institutional research wants to predict a college GPA, the first year GPA actually based on high school GPA and SAT square, and based on prior information there is well-established meta-analysis on this, I guess, and the high school and SAT score basically explain 27% of the variation in college GPA. So that is the information we do have. But from top officials, they do ask that how many sample size do we need to detect significant R square for 18% of power with alpha is equal to 0.05 and for admission policy. So we're gonna to suggest a sample size for this project or maybe for top officials for pupils executing this stuff. So to do this stuff, yeah, my parameter of interest is R square. If I do have R square, I should have to calculate Cohen's F square. Cohen's F square is effect size that we play with when we deal with linear regression and we wanted to change the effect of a coefficient of determination, and Cohen F square is equal to R square over 1 minus R square. So I will recalculate that one and I will just switch to my G power. Switch to my G power. So if I calculate my effect size, which is F square, is 0.37, which is 0.27 over 1 minus 0.27 is equal to 0.37. And I set already my alpha into 0.05. I usually set my desired power into 18%. You can make it 90, 95. And how many covariates do I have? I do have two, which is high school GPA and SAT score, which is Scholastic Aptitude Score Test. And if you simply calculate and you will get it 13 students are required to deal with or maybe to answer the request comes from the top officials, So I will repeat the same exercise using R, but using a different function under the package of power, So in case of ANOVA, I used power.ANOVA test, but here I will use it power.f2.test. Yeah, in bracket, I do have a parameters I should have to know very carefully. U is degree of freedom for the numerator, which is equal to the number of predictors included in the model. V is the degree of freedom for the numerator, which is n minus k minus 1. Just I should have to know the maths behind. And f2 is my Cohen's f square, which is calculated r square over over 1 minus r square, which is 0.37. And significance level is my type 1 error, and my desired level power is zero point 0.8. Yeah. Once you set, or maybe once you know this stuff, the only thing that you can do is simply running, and you end up with the same result. Here, where do I get my sample size for this case? Here, if you see this number, which is 26, I say that V is the degree of freedom for the denominator, right? The degree of freedom for the denominator is simply the number of observation minus the number of predictors included in the model minus 1. And I can just switch these formulas, and I can calculate my sample size, which is equal to sample size equal to V plus U plus 1. And I can get it around 29.2. I can approximate to 30. So which is basically the same result with the previous one that I obtained using GPower, So here, what you should have to know is that what I have, what I don't have, what is the research objective, and again, should I have to recalculate some transformation before I go to my G power, or maybe R. Basically, in R you can do all math by your own, which is very flexible, but G power is not this much. So the only thing that you can do is simply understanding the research question, and what's available and what is needed and what's not needed. Okay, if I do have R squared, I can play in such a way. What if my interest is to see a significance of a specific coverage on my outcome? Let's say, what is the significance of SAT score after just controlling uh, the high school GPA, let's say? Or maybe what if I may compare the full model with a reduced model? Am I capable to do this stuff? Yes, I can. But for today, I will simply just talk about just testing a significant effect for a certain cohort. Let's say my recent intention is to study the influence of average time spent per day exercising on BMI after 6 months. My assumptions are I do have a standard deviation for my X is 7.5 minutes. And again, standard deviation for my response or maybe outcome variable is 4. I usually set my power into 18%, and I usually set my type 1 error into 0.05. Good. And I'm going to calculate my sample size that helps me to detect the drop of BMI by 2 per 30 minutes. So that is my beta is equal to 2 by 30 is equal to 0.0667. So to get this effect, how many patients should I recruit? That's the question should I ask myself. So I do have beta. I'm dealing with beta, not R square here. So I should have to do some transformation before I run to my G power or maybe my R. So actually you can use also SAS or maybe other available software. Using R or maybe G power is not the must. In case of a linear regression model, if you are dealing with one predictor, R square can be calculated in such a way, and I found 0.016. And I should have to get my Cohen F square, which is equal to R square over 1 minus R square, which is equal to the same number, because 1 minus this number is 0.9 something something, and if you divide some number with number equal to 1, you may end up with the same number. That's why I give approximately the same number. So I will jump to my G power, just carefully plug in the information you have, and just click on the calculate, which is very straightforward. You need around 400 93 students, or maybe uh, uh, not student actually. My example is on influence of someone doing an sport or to reduce BMI. I may need around 493 customers to find an effect of a reduction of minus 0.0667. So I do have one predictor. uh, I can do the same thing. I have nothing to explain here because everything is the same. The only thing is that just adjusting your parameters using the function called power.f2t test function, and everything is the same. Now you end up with the same sample size. So before I close my today's talk, I may give some general, yeah, cheat sheet, I would say, in Power Package. I mostly wanted to just work on R because of, yeah, G Power is very limited. If you are only dealing with very specific and common steady design, of course, you can use G Power, but uh, sometimes you may deal very complex model and very complex design. In that regard, R is the place where you can do every stuff by your own. So, if you are conducting the following test, these are the basic explanation that you can get for power or maybe calculating sample size. Now, I am not saying that power package is the only package that you can use to calculate or maybe do power analysis in R. No, there are a lot of packages that you can use, but I mostly rely in case I do have some standard design. Now, as a final point, which are basically very important, and the message of this presentation is simply sample size justification is design specific. I cannot directly use a sample size that I can implement on independent t-test on linear regression because things are, yeah, applied in different setting, and my effect size are different, so I should have to be very careful which design I'm going to use. So again, at the same time, justifying your sample size is very critical and important for reproducible and transparent research. And I, if for instance I'm invited to review your paper, and if you are clearly stated your sample size justification, I can possibly start trusting you. But if you are hiding or maybe running through methods without explaining your sample size clearly, I may try, just you can't convince me, and so you better justify your sample size and power analysis in the best way possible so that one can trust your study and it can be reliable at the end of the day. And in one way or maybe in another way, you cannot contribute into the reproducibility crisis. That is point number one. Number two, effect size choice and assumptions are very critical. So, am I dealing with coincidence, f square, whatever? You should have to, yeah, fix it, the type of the effect size you are dealing with, and what are the underlying assumptions, what are the limitations. That's it. And software cannot replace scientific judgment. Of course, we do use software for sake of speeding up things, but they cannot replace your knowledge or maybe as the scientific judgment. And again, in some cases you don't find built-in functions and you are dealing with on complex models like repeated design, longitudinal, mixed effect, blah blah. So in that regard, the best strategy is to switch to the simulation, and in that regard you may get your sample size that you are required for it. So shortly, this is my talk. Thank you so much for your patience, and these are the references that I used. If you have any question, please welcome.